All right. Oof. Okay, and we are back for the second half. Let me go ahead and pull up my here. Let's get rid of that. That's good. Let's go here. Done. I think I got everybody, so that's fine. Let me share my screen. Start the broadcast. Awesome. Optimize for video. That's sharing. Okay. And we'll work here. Let me give it a moment. Okay. Well. Okay. Let's see what can I do. There we go. I'm just waiting for the confirmation. So like it's doing the thing again. Okay. Yeah, let me reboot. Let me push the signal again because I don't think it's showing the image. So if I stop the screen share, come on, where's my notification? Let's go. Come on, thank you. Let's try this one more time. Share the screen. I don't know why I need to do that, but that's how it behaves a lot of times. You just have to like re-push the signal for it to work. Okay. Let me see. Let's try this one more time. Share the screen. I don't know why I need to do that, but that's how it behaves. You just have to like. Okay. It's there. Come on. I don't know. It seems like it's still not pushing my image. It's there. Yeah, it's still not showing my image. Sorry, guys. Let me try. Maybe it's Notability. Let me just reboot Notability. I can close this and that. And let me just re-push the signal one more time. Let's try this one more time. Share the screen. Okay, that's fine. Start the broadcast. Like this. Okay. Now, if I can see this, I know it's working. Let's see one more time. Let's try this one more time. Share the screen. Okay. There we go. Finally, we got it working. Reboosting the signal before it works. But anyway, okay. So it's looking good. I got my confirmation so that I know that you guys can see my screen. I don't want to just launch into it and you guys can't see what I'm writing. Okay. Anyway, so I think this brings us at least officially like together to the close of chapter 1 on differentiation, right? So this section is section 1.8 on higher order derivatives. Higher order derivatives. A few objectives here. So welcome back. This is the second half of today's lecture, right? Objectives here, we like to find derivatives of higher order. Given a formula for distance, velocity, Given a formula for distance, find velocity and acceleration, right? The find is what I was missing. I was like, why does it sound weird? So given a formula for distance, find the velocity and acceleration. Okay, so higher order derivatives. We like to consider the function given by, let me get my pointer, come on. So consider the function given by this guy, right? We have this trinomial. Its derivative is going to be, the power comes down, right? And then subtract 1, and we get this result. So the derivative function f prime can also be differentiated. So we took the derivative of the original, we got this result, but then notice that this result, we can also take the derivative again, right? So we can think of the derivative f prime as the rate of change of the slope of the tangent line of f, but it can also be regarded as the rate at which f prime is changing. That's fine. All right, okay. All right, so the main thing here was that it is possible for us to take the derivative of the derivative in this case, right? So then we use this notation double prime for the derivative of the derivative, right? So f double prime just means the derivative of the derivative. F double prime d by dx of f prime, all right? So we call f double prime the second derivative of f. So for this y, if we took the derivative twice, we take the derivative once, we get an answer, then we take the derivative again on that answer. In this case, we got this result, right? This is called the second derivative of f. Okay, second derivative. And so it's just a derivative of the derivative, okay? So for higher order derivatives, we use a notation where we have this parentheses in, right? To express the nth derivative of f, right? The third derivative of f, third derivative, right, is this guy, fourth derivative, fifth derivative. You can't take it forever because if we try to go one more step, if we try to go to the sixth in this case, the sixth derivative, see, notice it goes to 0. Okay, and so the nth derivative of f is going to be 0 when n is greater than or equal to 6, right? So we can't, in this case, we can't go higher than a sixth order derivative. Okay. All right, but the whole gist here is that we can take the derivative of the derivative a certain amount of times. Okay. So Leibniz notation for the second derivative of a function is given by now. So given some y equals f of x, this is going to be read the second derivative of y with respect to x is essentially like you're saying d by dx of the derivative. All right. Again, this is read the second derivative of y with respect to x. The 2's in this notation are not exponents, right? So it might be tempting to like square. These are not powers. This just means the second derivative of y with respect to x. In other words, take the derivative twice. Okay, Leibniz notation. Okay, let's keep going. So I guess is that we did this one already. Okay, we're gonna let that be. So with this example, we're asked to find the second derivative of y with respect to x. Okay. So, okay. So let's see. Let's do dy by dx. Okay. I'm gonna look at that instead of 1 over x. I'm gonna look at that as. Are you hungry? You must be hungry. She's just like, get down. She's looking for. She's like anything she can find on the ground. She's just. Now with this 1 over x, I'm gonna look at it as x to the minus 1. Right. Let me write it over here to the side. So 1 over x is the same as x to the minus 1. I'm going to take the derivative of that guy. So that means my minus is going to come down, and that's going to be x to the power of, now if I subtract 1, it's going to be minus 2. Okay. So then when I go to take the second derivative, so the second derivative of y with respect to x, that's going to be d by dx of this guy, this negative x to the negative 2. Okay. So if we just apply the derivative again, the minus 2 comes down and becomes positive. We subtract 1 from the power, it's going to become negative 3. All right. So then ultimately we get 2 over x cubed. 2 over x cubed. I think we set it to 5 last time. Copy. Okay. So the second derivative of y with respect to x, 2 over x cubed in this case. And you see it here at the bottom of the screen. Okay. So for this y, find the first derivative and the second derivative. Okay. So for this y, let's see. So our y prime. So we need to apply the chain rule, right? The 20 comes down. We rewrite the inside. Let me clean this up. Then subtract 1 from the power. Then we're going to say times the derivative of the inside function. So that's going to be what? 2x plus 10. Okay. All right. So now we can already see If we go to take the second derivative, now we got to apply what the product rule along with the extended power rule, right? All right, so let's just take our time. So we got a second derivative. So the main operation here is multiplication, the product rule first times the derivative second plus the second times the derivative first. Okay, so the first is this. First times the derivative of the second is just going to be 2 plus the second, which is this, times the derivative of the first. All right. So 38, right? 380. So we get 380 x squared plus 10x. I think that's going to be what now, 18, because we subtracted 1. Kind of running out of space here. I'll just continue down here. Times, we got to say what? 2x plus 10. I think I got everything. Do we have like terms? We do have some like terms. Okay, let me get all of this on one line first, since I can move stuff around on this device. I was this close from eating breakfast at Spelman's cafeteria this morning. I was over there. I was like, I don't know. I just decided not to, for whatever reason, no reason. I don't know if you guys ever watched Different World, but that was based. I think it was. I mean, it's basically the AUC. I think it was Spelman's campus, or maybe it was Clark's. It was one. It was either Spelman or Clark. And I don't know if Dr. Cooper is still on campus, but Dwayne Wayne was based on him. Supposedly, that's what he told me. And I think they were filming when he was a student there, right? So this is interesting. Okay, so we got this. Let's see. I think we can kind of like do a little bit of factoring here. Let me see if I can highlight.
Professor,
Yes. Did I miss something?
how do you get the second derivative of the first derivative?
Wait, how did I get both of them?
Yeah, because I'm confused on how you get the 380 from.
Okay, the 380. So with the second derivative, right? We say the first times the derivative of the second plus the second times the derivative of the first, right? So the first is this guy. You see it right here. So the derivative of the second, the derivative of this guy is just 2. You see that right here. Then we said plus the second, you see it here, times the derivative of the first. So the derivative of the first comes from here. 19 times 20, that's where the 380 comes from. And then I repeat the inside. This is 18 right here. And then we got to say times the derivative of the inside function, which is 2x plus 10. Okay. Let me try to wrap this one up because I need to make sure that I did it right. I didn't miss anything. So let me see if I can highlight my like terms. So they both terms have this x squared, this guy, and they both have, am I missing something? They do not both have that one, but they do both have the x squared plus 10x, all right? Okay. So we can factor, they both have at least 18 of those. Let me see. So I could factor out x squared plus 10x to the power of 18. And what that's going to leave us with, now we could factor out some 2's. There's a 40 there. Let's see. Greatest common factor between 40 and 380. Hey Siri, what's the greatest common factor between 40 and 380?
The greatest common factor of 40 and 380 is 20.
20, right? We can factor out 20 from both of those. Let me see. What is that, a 19? Okay. So I'm going to factor out 20 from both of those. I'm thinking it says that's the thing. Makes sense. So I'm gonna highlight as a common factor, right? This has 20 along with that here. So if we factor out 20, I'm gonna put it here in front. Okay. So then that's gonna have a 2 that persists here. We still have this x squared plus 10x, at least one of them here. Okay. I'm going to say plus. Okay. Now it looks like we have this 2x plus 10 squared. Let me see. There's a 19 in there. So there's a 19 here. I'm going to just go like this. And I think that's gone, right? Because we took 18 of those. Okay. Now we can expand it a little bit further. And sometimes they don't do all of this. All right. I think this looks pretty good though. Let me see. I think I'm gonna go ahead and expand that and combine like terms. Okay. Let me just expand it. Okay. This 20 is going to persist here. We got this x squared plus 10x to the 18. So then this is going to become 2x squared plus 20x. Okay. We're going to have our 19. If we FOIL there, that's going to be 4x squared plus 40x plus 100. Okay. Now they might not have gone this far. I'm going to try to get it on, finish this out on the next line. Okay, so I'm going to try to make this be my last line. So we got our 20, we got our x squared plus 10x to the 18. Okay, so then with this one, 19 times 4 is what? 40 plus 36 is 76. So then let's put 78. This is going to be 78x squared. And then 19 is like running amok. 19 times 40, let me see. So 40 plus 36, 76, so 760. So 780, right? I think that's 780. So we're gonna go 780, I think that's okay. X. So basically what I'm doing, I'm distributing this 19 and then combining my like terms, just trying to get to the final result. Okay. And then 1900. Okay, we're gonna cross our fingers. Let's paste. Let's put this here. Okay. Okay, we're gonna leave it like that. Now I think there's some common, we probably could have factored out at least the 2 from all of those. 35, 39, 390. I mean, we could factor, let's go ahead and factor out that 2. If we factor out a 2, then this is going to become a 40. Okay. That's 78 is going to become a 39. 780 is going to become 390. Okay, 390. And if there were 1800, that would be what, 900? So 950. So 950. Okay. All right, let's see how do we do. God is good all the time, right? Because like you have to like, it's like a time warp happens. You have to like slow things down, focus, space it out, but we got it to the T, right? And that's no small. Look, you got to celebrate your small victories because you get plenty of defeats in this realm, right? But I'm just showing you that it's possible. Now, obviously, just do the best that you can, right? I don't want you to just do the best that you can. Whatever you need to do, just do it. Like it's going to be okay. This is why I do my unlimited attempts, because some of this stuff does get it's very easy to like lose track and be intimidated and like to shut down, which is what I'm trying to avoid, right? So that's why I do unlimited attempts. I'm telling you the 10%. I wouldn't even stress about that. Just try to get that stuff in there. Like keep it moving. All right. Okay. We are pretty much on track. Quick checks. Any questions? Do we need to go back? Just stop me if we do. I know that was a little intense. And like the thing about this, okay, let me do this other disclaimer. It's hard to follow anybody else. It's always hard to follow somebody else's work, right? I don't want you to try to follow what I'm doing to a T. I want you to just watch what I'm doing and just get ideas. But you don't really get it until you try it yourself. If you're trying to learn from what I'm doing, it's gonna bore a hole in your head, right? And it'll like drive you insane. It's not fun. So don't stress too much about, because you're not gonna see it trying to follow me. You won't see it until you do it yourself, right? So this is I like to say it's an art of discovery, and it's basically each person getting intimate with the information. But again, you don't really see it until you try it yourself. The quick check I leave as an exercise for you. Okay, so let's keep going. Okay. Now, okay, so we have this application of higher order derivatives. We have this definition where the velocity of an object that is now S of t is going to be our position function, right? This tells us the position of our object based on time. So S of t units from a starting point at a time t. So the velocity of an object is going to be the rate of change, like speed is miles per hour. Velocity is the rate of change of your position. So again, our S of t is our position function. When we look at the derivative of the position function, it gives us the velocity. Okay. Now this is just the limit definition. Limit as h tends to 0, so small change, right? This is the limit of the difference quotient. But the main gist here is that the velocity is the rate of change of your position function, or the derivative of your position function. Okay, that's the main thing here. Okay, so the velocity is the rate of change of your position. Acceleration is the rate of change of your velocity, like how quickly you're speeding up or slowing down, right? Right. And so, long story short, the acceleration is the second derivative of your position function. So given a position function, you can find the velocity by taking the first derivative, and you can find the acceleration by taking the second derivative. Okay. You could even verify the acceleration due to gravity being, what is it, 9.8 meters per second squared. You can, in a lot of examples, you can verify that it works. So given a position, if it's a free falling object, yada yada yada. Okay. Let me see. We got a solid 10 minutes. Let's keep going. So for this position function, find the velocity and acceleration, where s is the distance from the starting point in miles and t is in hours. Then find the distance, velocity, and acceleration after 4 hours. Okay. Let me give myself some space. I might not need it, but I feel like I might need it. So I'm going to give myself some space. Give myself some space and some grace, Lord. Come on. Come on. Oh, shoot. Now my device wants to throw a tantrum. And it does this. Okay, I forgot it does that. Okay. So let me reboot this. Space and grace, right? Not that. Okay. Let me just go back. Are you still throwing a tantrum? Come on. Thank you. Let's see, is this where we left off? Higher order derivatives. We were kind of towards the end. Thank you. We were working on this example. That we're trying to, where'd it go? This one. Let's add a page. You still gonna do this? I forgot what I need to do to get this to work. Oh man. And I think it involved rebooting my devices, which is what I'm avoiding. But I think it would work if I do it. Come on. Just add a page. Like, it's not that difficult. This is eating up a precious time. Come on. Are you gonna allow me to add a page? All right, we're working here. Let's try this again so we can get this last one in here. Simple, thank you. All right, cool. Last attempt. Add a page. Come on, add a page. Okay, let me I'll be right back. I'm gonna have to reboot my Zoom. I'll be right back. Hang on, guys. Let's see. Okay, that looks good. Oh, I forgot to let me reboot this. Okay. Okay, looks good. Optimize. Okay. All right, let's try this again. I think After fixes that as well. So it should work this time. Like I said, it's just temperamental. Like it's just like that sometimes. But stuff like this is why I do limited tips and stuff. Right, where is it? This one. I don't like that feature. Add a page. Oh, come on. Come on. All right, I don't know if we're gonna be able to do this one together. I'm gonna try a couple more times. Let me do one other thing that I think will work. I'll be right back. Let me do this. Stop my screen share. I'll be right back. Hang on. And the thing I know that will work that I'm avoiding is rebooting my device because we're at the end. I'm just trying to wrap this up. Let me go here. Okay. This one right here. Let me add a page. You still not gonna do it now? Yeah, guys. All right. Okay, I know what I can do instead. It's just I don't know why they won't allow me to add a page. But I have something I could do. Oh, let me try it first. I'm watching the clock. I know we're just about out of time. Yeah, and it's like there's no reason for it to not do that, for it to not work. Let me see. Can I copy this? Can I copy and paste? See, that works. Whatever. That's all I needed anyway. Let me cut this. Yeah, that's so weird. Like I don't know why it does that right here. I want to paste. Okay, let me do another one. Paste. Okay. All right, guys. Let me go to view seamless. Okay. And let me pull my image back up. Here, as we have a solid 5 minutes, I'm going to take advantage of it. Share the screen. Start the broadcast. Okay. All right. So hopefully the image will be pushed. You know, I was able to add the page. It was, I don't know, throwing attention, but it's fine. But this one shouldn't take us too long. That's how I was trying to finish it. Okay. Come on. I just want to get that confirmation that my image is there. Okay. All right, it's looking good. Okay, let's finish it up. Thank you. Stop. Oh, wait. Oh, come on. Can you guys see my screen? Play.
Yes, sir.
Okay. Play. All right. Okay, I think it's just go live. Okay, cool. Okay. Okay, so for this position, sorry about that. Yeah, it's just technology being temperamental. We might be in Mercury retrograde or something. That's what they always say is that, you know, when technology is going haywire, it's because of Mercury retrograde. Anything going wrong in your life, Mercury retrograde. That has nothing to do with anything. Okay, so for this position function, velocity is going to be the first derivative, acceleration is going to be the second derivative. Okay. Let me see. Okay, so let's write. So we got our position function, 10t squared. So that means our velocity function is going to be s prime of t. That's going to be 20t, right? And then our acceleration function, which is going to be the derivative of a velocity function, which is going to be the second derivative of our position function. Let me kind of move, let me drop this to the next line. Okay. This is going to be, so if we take the derivative of that result, we get 20. I guess we could have kept it on one line. It wasn't that much more. Okay. So we have our position function, velocity function, acceleration function. Then find the distance, velocity, and acceleration after 4 hours, right? So then S of 4 is going to be 10 times 4 squared, 160 miles. Okay. The velocity after 4 hours is going to be 20. Come on, where are you? 20 times 4, which is 80 miles per hour. Okay. We didn't even need all that space. I went through all of that to create some space. We got it on there. Oh my goodness, that is too funny. The acceleration after 4 hours is going to be, that's 20 second squared, miles per hour squared. That's the rate of change of your speed. So yeah, anyway. Okay, so we got these results, right?
Professor,
Go ahead.
for the acceleration function, why is it 20 miles per hour squared?
Those are the units for acceleration of miles per hour squared. That's like, I want to say that's, it's the rate of change of your velocity. So it's saying that your velocity is increasing by 20 miles per hour every hour, something like that, right? But you know, distance per time squared, those are the units for acceleration. And it's the rate of change of your velocity. It's how much you're speeding up at that moment in time, right? It's the rate of change of your velocity. Let me copy and paste. Let me confirm that we got these correct. The number 20 comes when we did our derivative, the variable drop off, right? When we had our velocity, when we went from the velocity to the acceleration, the variable was gone. So that means it's a constant acceleration. It's steadily increasing at that acceleration. All right. Okay. So we got 160, 80, and 20. Let's see. And we can get rid of these other pages. Didn't even need, I did all that. Delete. And delete. And then we go to view, single page. Okay. All right. So I think we have a type version of everything here. The velocity was 20, acceleration was 20, 160 miles. At that position, we're doing 80 miles per hour, 20 miles per hour squared. Okay, I think that's it. Quick check again, we usually leave as an example for you guys. And that officially, you know, at least brings us to the end of chapter 1. We are rapidly approaching exam 1. Now, you know, my college algebra courses, they're taking their exam this week, but you guys are a little bit different. So your exam 1, you can anticipate it during week 6, right? It's gonna cover chapters 1 and 2, and we will get through chapters 1 and 2 in time for the exam. I know this is a little bit behind the homework. I'm not gonna, you know, I'm not gonna let that 10% get in anybody's way. Not on the homework. Now, again, we're gonna get caught up on the exam. That's a little bit different. But I'm not. This 10% of 10% is like 1% overall graded. It's nothing, right? And I mean, it goes deeper than that, but that's neither here nor there. Yeah, so on Wednesday, we'll go ahead and get started on chapter 2. the goal is to do 2 sections from chapter 2 on Wednesday. Are there any burning questions before we go our separate ways? Any burning questions? Okay. If there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your evening, guys. Take care. Peace.
Professor, can I speak with you after class is
Or
over?
Does it need to be private?
Yes, sir.
Still got
Okay,
that thumb up the wrong.
Okay. Let me stop the stream and we can talk about it.